Okay, so now we are going to talk about enzymes and enzymes working as catalysts, which will increase the speed of reactions. So, how do enzymes work? The actions of enzymes are going to begin with the enzyme-substrate complex. So, the enzyme-substrate complex is where the enzyme and substrate bind together. The substrate must bind in the active site of the enzyme, and we've already discussed the different structures of proteins, primary, secondary, tertiary, etc. All are very important in forming that active site and forming that enzyme-substrate interaction. So in general, the active site is a very small portion of an enzyme, and the amino acids within the active site might be very distant on the primary structure. So there are certain amino acids that we talked about that can be part of the active sites. We have serines, we have histamines. So on that primary structure, which is the linear peptide sequence, for example, you have your amino acids, right? All your amino acids in a peptide. And you might have your active site amino acids here and here. And so this is the primary structure and they're far apart. And then when it folds into the tertiary, so it goes to a secondary, and then it goes to the tertiary, etc. These active sites fold together, and it's really the interactions between the amino acid side chains that are going to help to bring the active site and form it. We also talked about the lock and key model. This can help to explain enzyme specificity, but not why a reaction occurs. And then we discussed the induced fit model, and this explains more how the enzyme specificity is for the transition state, and that helps to explain why the reaction can proceed. So the substrate binding to the active site, again, it has to bind to it, but it's really going to be that binding that changes the interaction between the enzyme and the substrate so that it conforms to the transition state of the interaction. Now, in rate determination, we are basically going to ask the questions of how fast is the actual reaction. So some things to keep in mind is that for most interactions, the rate reaches saturation on a hyperbolic curve. And so remember those curves we were talking about with hemoglobin, myoglobin, and myoglobin was the hyperbolic curve. And so in general, addition of substrate will increase the reaction rate until there is saturation. And at the period of saturation, of course, when you add more substrate, you're not going to increase the rate of the reaction. So when we do plot the reaction rate, which is velocity, versus the substrate concentration, we can get information about the reaction. And this information is going to lead to some information about the velocity maximum as well as 1/2 velocity maximum, which is referred to as the Michaelis Constant. So when we do this plot, I'll do this, which is velocity versus substrate concentration. And the 1/2 Vmax is going to be the Michaelis constant, which we'll talk about in just a moment. And this constant is really telling you what is the concentration of the substrate that produces a rate of 1/2 the Vmax. So 1/2 of your enzymes are bound to the substrate. Okay, so you're going to have the Michaelis constant be a rough measurement of enzyme substrate affinity. And I said rough substrate because it is not a very precise measurement. And basically at very low substrate concentrations, the relationship between the substrate and its velocity, being that it can find enzymes that it can bind to, is going to be linear. So when you have low substrate concentration, velocity is linear. And you can think of it as it's easy to find enzymes to bind to, so they're not saturated. And then at high concentrations of substrate, the reaction approaches what's called a zero-order kinetics. And zero order basically just means that it is no longer dependent on the concentration of the reaction. So the rate of the reaction is independent. Of the substrate's concentration. Now this region between the zero order, when you almost are at saturation, and the first order, in which you are adding more substrate and you're increasing the rate of the reaction, are very hard to interpret. And so it's really easy to say you're at saturation, it's really easy to say you're not at saturation, but anything in between gets a little bit more complicated. So Michaelis and Menten came up with an equation to help to measure enzyme behavior. And this equation works best for regulatory enzymes that are also what we call allosteric enzymes. So their equation is going to measure enzyme behavior. And it's best for regulatory enzymes that are allosteric. Now this is the Michaelis-Menten equation, and this is actually from your book. And so of course E is going to be the enzyme, and then you have S is going to be the substrate. You have the ES, which is called the transition state, which is the enzyme substrate complex. And then you have, of course, the product that you're trying to make. And the K are the various constants at various steps. So this is the rate constant. And a negative indicates a reverse. Okay, so apart from this, we have a few other things. We have the V. So V is the velocity or the rate of the reaction. And then we also have Vmax, which is the maximum reaction rate. And then Km is going to be that Michaelis constant. Which is basically a measurement, a rough measurement of the affinity of the enzyme and the substrate. And so we'll look at this a little bit more. Your book has the equation enzyme substrate where you have K1 forward and K -1 reverse goes to the transition state, which is this enzyme substrate complex. And to make it very simpler, forming the product is going to be favorable. So the reverse isn't shown here. So it will move towards the enzyme releasing the product. Now, in most situations, though, the reverse is going to be possible. So in the first step, you have the formation of the enzyme substrate transition state complex. And keep in mind that several reactions might have more than one of these transition state complexes. It might have to go through several steps to get to the actual product. But in general, the enzyme and substrate will combine to form this enzyme substrate complex. And then after this forms, it could break down. So you could get it breaking down, right? And so this would be K -1, or it can proceed to the product. And this would be dependent on the K2 enzyme, so the enzyme substrate going to the product. Now the formation of the enzyme and product, it can go in reverse direction. So K2, or the enzyme that is going to catalyze K2, can go in reverse, and you can go back to the enzyme substrate complex. So this is the K -2. Now, most times in biological systems, this is ignored because you're trying to push towards the product, but many enzymes can go in the reverse directions. And all of these Ks are just simply rate constants. How favorable is it to move to the product? How favorable is it to go back towards the substrate? Okay, so in general, Michaelis-Menten kinetics are going to help to explain your reactions. And so you're going to have a mathematical reaction. So you have your velocity. So basically, you're trying to reach a substrate concentration in which you have 1/2 of the maximum reaction rate. So that's 1/2 Vmax. And in this situation, the concentration of your substrate is going to be equal to that Michaelis constant, that Km. So the math behind this is V1 is Vmax of the concentration of your substrate over the Km, that Michaelis constant, plus the concentration of your substrate. And so this is going to equal Km, which is 1/2 Vmax. I should put this in rearrangement, equals the concentration of your substrate, so you bring that factor out, over Vmax over V1 minus 1. And then you're going to get Km. It's going to be equal to the concentration of your substrate over Vmax V1 which is turned into Vmax divided by 2. Make these brackets a little bigger. and this is to the -1. And then this is going to give you Km equals the concentration of S times 2 minus 1, which is Km is equal to the concentration of S. And so the Michaelis-Menten equation is going to give you a hyperbolic plot for your reaction. And so with this hyperbolic plot, you're going to get a few things that you can take away from this. And so one of those things is that we, of course, have our Vmax, and it's not really showing it here. It would be out here. And remember, this is going towards enzyme saturation. Okay, and then you have your 1/2 Vmax, which is going to give you the Km, which is that Michaelis constant. And again, it's the substrate, the concentration of the substrate in which your velocity is 1/2 your Vmax. Now, basically, we have three things going on here. We have this position A, in which you have the rate of the reaction is directly proportional to the substrate. Right? So there's no enzyme that is being bound, so the substrate has full access to enzymes. And so the rate of the reaction will be increased as you increase the amount of substrate. And then you have the period of B, which is 1/2 Vmax. And that's where you have your affinity or half of your maximum velocity of the actual reaction. And then you have C over here somewhere, and C is the rate of the reaction becomes a zero order reaction, and so it's not going to be dependent on the substrate. And so, of course, A was a first order, and then all the stuff in between is a combination. And so they get a little bit harder to explain mathematically very easily. Okay, so what can Vmax and Km tell you and what can they not tell you? So they can tell you, they can be important in comparing different enzymes, so they can compare enzymes. We'll see that in a little bit. They can be useful to determine if reactions are simple or complex. Now, what can they not tell you? They cannot tell you the number of reactions. They cannot tell you the rates of the reactions. And they can't tell you the chemical nature of the reaction steps. Okay, so an example of this is you can use these plots to see differences in isozymes, for example. So here we're showing a plot of hexakinase 1 versus glucokinase. And the substrate for both of them are exactly the same. So they're both going to be able to phosphorylate glucose. So these are both going to be referred to as isozymes. So they are enzymes that can work on the same product, however, they are expressed at different sites. So hexakinase 1, not surprising, it has this hyperbolic, is going to be expressed in our red blood cells. Remember, red blood cells can only do glycolysis, So they have to have a higher affinity for glucose because that's their only source of energy. So they need to use glucose. So the Km for our hexakinase 1 is about 0.05 millimolar. And then when we look at glucokinase, glucokinase is an isozyme of hexakinase. And this is found in the liver and the pancreas, and especially those beta cells, which are going to be sensitive to high levels of glucose. And so the liver and the pancreas have very different function with glucose than the red blood cell. Red blood cell uses it for energy, so it needs it. Glucokinase in the liver and pancreas want to sense a higher level of glucose because remember, in the pancreas, you're going to release insulin in response to glucose. In the liver, you're going to start storing glycogen in response to glucose levels. So you don't want to have them have a high affinity for glucose because you need to spare the glucose during fasting for your red blood cells. So in the liver and pancreas, glucokinase has a Km of about 5.5 for glucose. So the higher the Km, the less affinity. Okay, so you can basically think about it as your glucokinase, when glucose is at low levels, it's kind of like, nah, I don't want to bind to you, I don't want to bind to you. But when glucose increases, then it's bumping into glucokinase so much, glucokinase kind of gives in and says, fine, I'll bind to you and I'll change you to glucose 6-phosphate. So during the fasting stage, your blood sugar is about 5 millimolar. About 90 mg per deciliter. And so the red blood cells can function even if there's very low levels of blood sugar glucose. And it's simply because they have this high affinity hexakinase 1, which gets saturated very quickly with low levels of glucose. Now, what is hexakinase and glucokinase doing? Well, hexakinase and glucokinase are both doing the same reactions as I said before. They're taking glucose from the blood and it's entering the cell, and you have the hexakinase convert glucose to glucose 6-phosphate. Remember, this is large and negative charged. And so basically, once you have phosphate attached to glucose in the 6th position, that's where the 6 comes from, that glucose is stuck inside the cell. And the red blood cell wants that. The red blood cell has to use that glucose. And the liver and the pancreas want it if there is high glucose, typically during a fed state. Okay. All right, so now to make your Michaelis-Menten equation more useful, it was converted into another type of equation called the Line-Weaver-Burke equation. And basically, you're basically going to take the reciprocal of the Menten equation. So you have your velocity, which equals the Vmax times your substrate, and this was over your Km plus your substrate. So for the Line-Weaver-Burke equation, you're taking the reciprocal. So you would be 1 over V, and this will be equal to the Km plus your substrate over your Vmax times your substrate. So you just flip it. And then you do some fancy math. So So we'll do some fancy math here. And again, we'll have our 1 over V, and this will be equal to Km plus or whatever you do to one side, you have to do the other, and then you can simply cross out your substrates on that side, and then this will give you, this arrow down, 1 over V sorry about that. And this converts this into y equals mx plus b. And this, of course, is the equation of a line. And so you've converted that equation from Michaelis-Menten into the line Weaver-Burke equation, which is the equation basically of a line. Now this is line Weaver-Burke is going to be, again, a ballpark approach. Now with computers you can get very, very specific, but in the past this equation was used to just give a general range. The line Weaver-Burke is also called the double reciprocal plot because we just took the reciprocal of the Michaelis-Menten. But the problems with this approach is going to be an overemphasis at the lower substrate velocities. And because of this overemphasis, you can only get a general idea of the Km and Vmax. And again, computers can calculate these precisely. But basically, the plot will give you a y-intercept. So let me get this. So you get your y-intercept, and this is going to be 1 over the Vmax. And you get an x-intercept, which is going to be 1 over your negative 1 over your Km. So now, if you're going to interpret your Vmax and Km, there's a few things. So the Km is, remember, it's an approximate measurement of affinity. Okay. And this is the affinity of the substrate for the enzyme. So the higher the Km, the less affinity. We just saw that with our glucokinase and hexakinase. So remember, our hexakinase 1 had a very low Km, so it had higher affinity for glucose. And our glucokinase had a very high Km, so it had a lower affinity for glucose. Now the Km is that Michaelis-Menten. This is the Michaelis-Menten, or it's called the Michaelis Constant. And this is the substrate concentration at which the initial reaction rate is 1/2 maximal. I can just put it in, you guys know this. This means concentration of the substrate. Okay, and so Vmax is a measurement of how fast the enzyme can go at full speed. It is the rate of the reaction. And Vmax and Km are going to define the kinetic behavior of an enzyme as a function of the substrate concentration. So the function to the concentration of our substrate. And so again, if you have a low concentration of substrate, you are basically at a first order. And then if you have 50%, or you're reaching the Km, that is where you have half of the Vmax, so half of your enzyme little pockets are full of substrates. And then you go to a zero order, in which you have saturation. Okay, so first order, you're adding more substrate, you're pushing the reaction forward, and then it gets to a point where their substrates are having a hard time finding empty enzymes, and so that's going to lead to a zero order or saturation. So what does all this mean? And so when we're talking about the rate of reactions, of course, what's important to understand are the kinetics of the enzymes are going to be similar in general. So the addition of substrates leads to what we call as a steady state. So when you add substrate, you go towards a steady state, which is in fact that enzyme substrate transition state. So this is true of all enzymes. And so the rate of this complex formation balances the rate of its breaking down. Okay, and as the substrate concentration increases, the steady state activity of the enzyme increases in a hyperbolic way as it approaches Vmax. Okay, and so the concentration of S is your Michaelis constant, which is Km. This is really relating velocity to the concentration of your substrate and the Vmax. So the Michaelis-Menten kinetics is also referred to as steady state kinetics. Kinetics. Okay, so your Michaelis equation relates velocity to substrate and Vmax. And then also Km and Vmax are going to have different meanings, of course, for different enzymes. So the limiting rate of an enzyme is going to be catalyzed by the reaction at saturation. And that's going to be described by something that's called Kcat, or the K minus, which is the turnover number. So let's see, limiting rate. and Kcat is turnover. And cat stands for catalyst. Now, where is Kcat coming from? Well, it's simply what we just are talked about earlier. So your Kcat is going to be where you have your substrate plus enzyme, and it goes to your ES. And then this breaks down into E and product. Remember, we had the K1, and we had a K minus 1, and we have a K2, and in this way we have a K minus 2. So at saturation, your minus or your negatives are also going to be called cat. So K minus 1 equals K1 cat, and K minus 2 equals K2 cat. So basically the turnover, or going backwards, is the Kcat, which is going to measure the catalytic efficiency. So are you really going to push forward towards the products, or are you going to go fall back to the enzyme substrate, or even further back to the actual substrate? Okay, so we're going to stop here and we'll continue our talk of enzymes on the next lecture.